Welcome to Bible and Breakfast. I've really been looking forward to this particular talk. And as you know, we are really blessed, have been blessed with some remarkable speakers, and this morning is no exception. If you were here last week, you heard really a fascinating presentation on the history of the alphabet of the Hebrew Bible and how the Hebrew language was able to spread biblical literacy here throughout the ancient Near East and down into modern times. Well, this morning I'm very pleased to introduce a very dear and long-standing friend of mine, Dr. Perry Phillips, who has remarkable background and training in a number of different fields, including astrophysics. He was a graduate student at Cornell, I guess, when people such as Carl Sagan and Gold and
Tom Gold.
Some notable astronomers here were teaching astrophysics. Also has a theological background, has a Master of Divinity from Biblical Theological Seminary in Pennsylvania. And he's also married to a very prominent Old Testament scholar at Gordon College, Dr. Elaine Phillips. And how many trips to the Holy Land has Elaine done, I guess?
Well, probably around 40 or 50, but we've led about 70 or 80 groups through Israel.
Okay, and so if you ever have an opportunity to do a Holy Land tour with the Phillips, you would just benefit from that greatly. But the topic today really is science and faith. And in the minds of many people here, sometimes there's a tension, if not a contradiction, between what can be known through the scientific method and the study of the natural world and our Christian faith. But on the other hand, I think as we'll see here, there's a way of looking at the natural world. There's a way of looking at our solar system, of our galaxy, of the universe, and indeed to come to the conclusion that the heavens, in fact, are telling something about the glory of God, the wisdom and power of God in the things that He has made. So let's pray together. The Lord be with you. Let us pray. Our Heavenly Father, we do believe that you are our Creator God. And as we, again, ponder the vast magnitude, the power, and also the remarkable design in your creation that makes our human life, our biological life, possible. So we pray that you would anoint our speaker, your servant Perry, and us, that our understanding might be enlarged, that our faith might be deepened, that we might serve you with confidence and joy. In the name of the Father, the Son, and the Holy Spirit, amen. So Perry, welcome.
Thank you very much. I figured that during Christmas, if people can wear Santa hats, then during the playoff season, I can wear my Green Bay Packer hat. At any rate, go Packers. Glad again to be here, and I hope you can hear me in the back. Can you hear me in the back? Yeah. Good, good. Anyways, design or chance in the solar system is the topic today. That's by me, and a lot of you have probably seen this already. So many people like to take selfies that I decided I would take a selfie of myself as well. So, hi folks. One thing I enjoy about PowerPoint is being able to add bells and whistles. It's a lot of fun. And what is really interesting with this particular talk is the template, which is called the fireball, and it fits in very nicely with astronomy. Well, first of all, why should we look for design to begin with in astronomy? And one reason is the world looks design, and one would like to know who the designer is. There is also, for Christians, it tells us something about God. And this is something that Jack brought out as well. It gives us some information about God from what we call His general revelation. Specific revelation meaning His Word, general revelation referring to what we can understand about God through nature. But why consider astronomy, other than the fact that I'm an astronomer? For one reason, I think it's a fascinating subject in and of itself. And those of you who are in biology, geology, sociology, psychology, theology will probably say the same thing about their subject as well. But astronomy is a very interesting subject, and it encourages ultimate questions. And what I mean by that is the following. There is an astronomer that you are probably not very familiar with. His name was Herbert Freeman. He was the one who actually pioneered sending rockets into the stratosphere and above in order to make observations, astronomical observations, because down on Earth with the atmosphere, there's certain observations we cannot make. And what he did is pioneer the use of rocketry. My advisor at Cornell studied under him, and I had the chance to meet him as well. And here's what he said. I do not know what his theological bent was, but he said it's impossible for any sensitive person to look at a star-filled sky without being stirred by thoughts of creation and eternity. The mystery of the origin and destiny of the universe haunts us throughout our lives. And I think if you've ever been away from the city and you look up into the sky on a starry night, especially if the moon is not there, and you look at all the stars, it's hard to imagine, it's hard not to imagine where all this came from, and maybe even what its destiny is. But not only is it a wonder to look at the universe and to see what's going on, also Scripture itself encourages it. Here's Psalm 19, which says, the heavens show us something about God. And what does it say? Psalm 19:1. The heavens declare the glory of God, and the skies proclaim the work of his hands. So even Scripture encourages us to look up. Second, Psalm 8. The heavens show us our own worth. And here's what Psalm 8 says. When I consider your heavens, the work of your fingers, the moon, the stars, which you have in place, what are people that you are mindful of them, or their children that you care for them? Again, when we look at how small we are compared to how great the universe is, and then we think that the God of the universe, the God who created all this, actually is interested in not us, but me personally. It really is quite a wonder. And then we also have Romans chapter 1, which shows us how much value God himself puts on what I said was general revelation. That is, the message that he gives about himself through nature. Well-known passage. The wrath of God is being revealed against those who suppress the truth by their wickedness. What truth? The truth that nature declares concerning God. What may be known about God is plain to them. God has made it plain to them, which is a very interesting statement. And then he goes on, Paul goes on to say, for since the creation of the world, God's invisible qualities have been clearly seen by being understood from what was made, so that all are without excuse. And basically what Paul is saying, a correct understanding of what we see in the heavens should bring us to an understanding enough about God so that we would seek to pursue what he has to say. Now, before I continue, I have a disclaimer. Some physics will be discussed. Okay? That's my disclaimer. But rest assured, no math. Okay? No math. Well, what has to be right about the earth for life? Because that's what we're really interested in. Here we are on earth. We have very complex life. Simple forms, complicated forms, the most complicated forms being ourselves, which is very interesting. Robin said something about Einstein, and he said the two things I don't understand are the working of the tax system and intelligent life on Earth, or something along those lines. I'll look up the quote directly sometime. At any rate, what has to be right for life to be here on Earth? Okay? What do we need? First of all, we need the proper location. And not only the proper location of Earth here in the solar system, but also we'll see we have to have the proper location of the solar system itself in the galaxy. And we'll explain why. Second, the planet that contains life has to have the right mass. That is, must be a certain amount of material there for life to exist. And you say, well, how can that be? Why can't the Earth be larger? Why can't it be smaller? Well, it can be, but there are limits, and I'll explain how that works. Third, we need a massive moon that is associated with a planet, at least with Earth itself. We need a massive moon for reasons that I will explain. Okay, it's not just to sing lullabies to your children or to a full moon in order to propose to your spouse, but there is a physical reason why a large, massive moon for the Earth is extremely useful, and without which it would be difficult to think of life reaching the heights that it has here on Earth. Continuing, the tilt of the axis of the Earth is important. And we will see an example of a planet in the solar system whose axis is very much more tilted than what we have, and what that would mean for seasons and how that might impact life. We need the right kind of star. You cannot have even a planet like Earth around any old star because of very disastrous things that could occur. And we'll take a look at that. And then finally, we also need massive outer planets in the solar system in order to protect us from what we would call, quote, space junk, end quote, that could have a huge impact on the Earth. So with all that in mind, and with permission to continue to speak until 1 o'clock, we will get started. First of all, the Earth's location. We are here. Not the scale, of course. This is supposed to be a funny cartoon, so laugh. Thank you. Okay, the Earth's location. We are the third planet from the sun. And the planet is in a good location, which I will explain. However, not everybody believes that the universe is large and that the Earth itself is not the center. In fact, there are some people who think the center of the universe is them themselves. And here's an example. These are the planets listed up here, solar system, and right here, in case you can't see in the back. Until I see evidence to the contrary, I will continue to believe that I am the center of the universe. Unfortunately, it's not just children who feel that way. Well, I'm going to discuss what is known as the habitable zone, and that is, what is the range of distance that the Earth can be from the sun and still have life pretty much as we know it, but from simple life to complex life. What is the range? The Earth is about 93 million miles from the sun, which astronomers call 1 astronomical unit. 1 astronomical unit is the distance that the Earth is from the sun. Venus is about 7/10 of an astronomical unit, and Mars is about 1.5 astronomical units. And when it comes to the solar system, we always compare things to the Earth. So when we say Jupiter, instead of saying it is 10 to a bazillion power kilograms or something like that, but we will say it's 312 times, 311 times more massive than the Earth. Or we'll say it's 10 times larger diameter than the Earth. When we talk about distances, we use the distance of the Earth to the sun. And that helps us compare things. And so what is the habitable zone? And you'll see that here in the green is the habitable zone. Here is the sun as it is now, about 4.6 billion years after its creation. And the sun evolves, by the way, and we'll see how that impacts life as we know it on Earth. But here is Mercury, Venus, here's Earth, here's Mars, and the green here, here's Jupiter, Saturn, etc. The green gives you the habitable zone. That is to say, it is the range of distance from the sun that the Earth can be where water will not boil away, i.e. the planet can't be too close to the sun because then all the water boils away. And second, it can't be too far from the sun because then all the water freezes. Let me state that differently. It's got to be the range from the sun in which water exists as a liquid, because we have absolutely no idea how life can exist as we know it without liquid water. Some people have proposed ammonia or liquid methane or things along those lines. We have no idea. We need liquid water for life to exist, and this is the zone in which water can exist as a liquid form. And so, as you see, it goes from a little on the far side of Venus all the way to a little beyond Mars. Now, that's just the temperature at which water can exist as a liquid. There are other things that are needed in order to define the habitable zone, and some of those I will get to. Some people feel that the habitable zone here on Earth for human beings may be about the thickness of this line. In other words, very small. We can be maybe about 4% closer to the sun and maybe about 10% farther away from the sun because other factors are involved, and we'll see what some of those factors are. Now, not only do we have a habitable zone here in the solar system, but we also need a habitable zone in the galaxy itself. Here's why. Our location in the galaxy. Here's a galaxy, and if you were to look at the Milky Way head on, from top down as you like, it looks like a huge pinwheel. Here, it is very close to what the Milky Way would look like. Here's the center. Here are the outer arms of the Milky Way. And the solar system is located on one of the galactic arms. Okay, that's nice. Let's look at side view. Here it is, an edgewise view of what the Milky Way would look like. And from that point, here's where the solar system would be. Now, the question, of course, is, so what? Here's a so what. We have to look at the role of supernovas in galaxies. Bear with me. What are supernovas? Exploding stars. Yeah, there you go, right? They're exploding stars. And they are so enormous, their energy release is so enormous that a supernova for a couple weeks can emit as much light as an entire galaxy that has, on the average, like our own galaxy, maybe 500 billion stars. And for about 2 weeks, one supernova can emit all that energy. You don't want to be around it. Might be nice on the 4th of July, but normally you don't want to be around it. And here is an example of a supernova that has gone off in a distant galaxy, and you see the amount of light coming from it is almost the same as the entire galaxy itself. All right. Here, by the way, is a Hubble photograph of a region of space called Eta Carina Nebula. And if we see a supernova in our own lifetime, in our own galaxy, this is probably where it's going to occur. It appears it's right on the verge of a supernova. Now, supernovas in life. Supernovas, in spite of their destructive activity, are absolutely necessary for life. Why is that? Here is what a star looks like before it becomes a supernova. It looks like onion. You have layers of an onion, and basically it looks as follows. The core becomes iron. I won't explain the process. The core becomes iron. As soon as the core becomes iron, some very, very disastrous things happen where the supernova explodes, but as it explodes, it throws out a lot of material into the surrounding medium. Iron, of course, that you have in the center, but then also some very, very critical elements. Carbon and oxygen. What else is needed for life? You need carbon, you need oxygen, you need nitrogen, you need hydrogen, of course, but that's already in the star. You need calcium, you need phosphorus, you need the iron for blood, right? Where did all that come from? It was not created at the creation of the universe. The only way that we can have elements like that in the universe are because of supernovas. Now, what happens is the supernova explodes. All this material is scattered out for thousands of light years. But not only do we have stars that explode, we also have stars that form through the gas and dust that's through the galaxy. When the gas and dust finally condenses into a star through gravitational attraction, and through that process, planets are formed, where does the dust, where does the dirt that we have on Earth today, where did it come from? Supernovas. In a sense, we are star stuff. I know it sounds woo, kind of new agey, but in a sense, we really are star stuff. Okay, so that's the connection between supernovas and life, but what does that have to do with our location in the galaxy? Here we go. Why is this important? First of all, again, here's where the solar system is located. In the spiral arm, suppose it were located in the center of the galaxy. Too many supernovas going off. It would destroy life. You'd have a lot of material there, but life would not get started because you would have too many supernovas going off. Suppose the solar system was too far from the center of the galaxy and it was not in one of these spiral arms, but way off in the distance. What's the problem there? Too few supernovas going off. Not enough material to form life. And so, where we are located in the galaxy itself becomes an important factor in terms of life existing here on Earth. So you see the connection there. Earth's mass. What do we mean by mass? The amount of material that's there. Okay, it's lightweight, but mass is the amount of material that is there. We need an Earth of a certain mass in order for life to exist on Earth, and here is why. First of all, there's a relationship between the mass of a planet and the amount of carbon dioxide that is in the atmosphere. Because carbon dioxide, as we know, produces what's known as a greenhouse effect on the Earth. In other words, carbon dioxide keeps the Earth warmer than what it would be normally without the carbon dioxide. And the atmosphere, as tried to show in this particular diagram, the atmosphere works a little bit like a greenhouse. Now, so what? Without carbon dioxide, the Earth would have frozen already. In fact, the Earth has maintained the temperature that it has because of the carbon dioxide that has been in the atmosphere from the time of its formation. If we didn't have any carbon dioxide that would warm up the Earth a little bit more than what it would otherwise, the Earth would be an ice ball. So carbon dioxide is necessary, but what does that have to do with the mass of the planet? First, what's the source of carbon dioxide on Earth? Well, of course, we're talking about human emissions, but I'm talking about through the history of the Earth, the source is really the degassing of the interior of the Earth. Early in the Earth was hot, many volcanoes, and we have them now as well, and that was the initial source of carbon dioxide. Now I'm going to get back to this later, source of carbon dioxide, but here is what is happening. As I said, you need carbon dioxide for the Earth to stay at a temperature that will allow water to exist in liquid form, to give you the right temperature, otherwise it would freeze. Here's what's happening. If the Earth were too small, only about a quarter of the mass that it has now, it would not have degassed enough carbon dioxide to warm up the temperature where water would be able to stay in liquid form. But suppose the Earth was a factor of 2 more massive than what it is now. Then you would have so much carbon dioxide that would have been emitted by the Earth that you would have what's known as a runaway greenhouse effect, which is what we have on Venus. Venus has a choking atmosphere of carbon dioxide. Venus, the temperature is about 900 degrees. The surface of Venus is hot enough to melt lead. Wow. Not to mention that the atmospheric pressure is about 90 times of what you have here. The same kind of thing would have happened here if the planet were too large and too much carbon dioxide had been released into the atmosphere. I mentioned previously the need of a moon. What is interesting is that if you exclude Pluto, the ratio of the mass of the moon to the mass of the Earth is the largest ratio of any other planet's moon to the planet. Okay, in other words, proportionally, the Earth has a larger moon than any other planet except Pluto. Pluto has Charon, which is roughly the same size as Pluto. It's almost like a double planetary system. But at any rate, the moon is a very significant part of our observations at night, and it has a profound effect on life on Earth. To wit, here's what's interesting. When we talk about the origin of the moon, as I said, it's critical, but it appears that it was an accident, quote unquote, in its formation. And here's what is the leading contender as to how the moon was formed. Early in the formation of the solar system, not only was mass accumulating, material accumulating to form the Earth, but the material was also accumulating to form other bodies. And all of them, of course, are swirling around the sun. And you're having collisions. And the leading contender for the formation of the moon is that we had as a huge object about the size of Mars that crashed into the Earth. And as a result of that, of course, a lot of material then was distributed into the region around the Earth, and through gravity, a lot of that came together, condensed, to form the Earth the size that we have, and then eventually to form the moon. And what you have is certain mathematical simulations of what might have happened, and it looks a little bit like this as we go from across like so. But you get an idea of what's going on. Here's the impact up here, and then stuff gets flown off the Earth. Eventually you get some of the material that collapses, some of it falls back into the Earth. Eventually, however, what you get is, as the material spins around, eventually what you get is the final moon. Now, the moon is about a little bit more than 1% of the mass of the Earth. On other planets, the moon is, any one moon is a speck of dust compared to the planet. By the way, the planet that has the most moons now is Saturn. It's around 82. Jupiter only has about 78 moons. And you go out to some of the other outer planets and they have a bunch of moons as well. But they are tiny. They are specks of dust compared to the ratio of our moon to the Earth. Well, again, so what? There are two so whats. First of all, the moon has tides, and those of us who live by the coast of Massachusetts know all about tides. You can get anywhere between an 8 and a 12-foot change in the height of the water. All right, how does that occur? Okay, bear with me now. Here's where we're going to do a little bit of physics. Here's the Earth. Whoops, there it is again. Here's the Earth, and we're looking at it from the North Pole, okay? When you're looking at the Earth from the North Pole, the Earth spins on its axis counterclockwise. Not only that, all the planets are going around the sun counterclockwise. Not only that, except for a few cases, the moons are all going around planets counterclockwise. Excuse me, certainly the case for the Earth, but it's also the case for most of the other planets as well. Okay, so what? The Earth is spinning on its axis much faster than the moon is going around the Earth. It takes the Earth 24 hours to spin once on its axis. The moon goes around about once every 29 and a half days or so. But here's what happens. The moon pulls on the Earth as the Earth pulls on the moon. In fact, it's the gravitational attraction that keeps the moon in its orbit. But the moon is closer to this face of the Earth than it is to the farther face of the Earth, okay? So therefore, you have a little bit more gravitational attraction on the side of the Earth facing the moon than on the side of the Earth that is away from the moon. So in a sense, this part of the earth is being pulled with a greater force than the earth itself, and the earth itself is being pulled with a greater force than the opposite side of the earth. You with me? Well, what does that mean? We have about 75% of the earth is water. So what it means, the pull, this tidal pull, raises a bulge in the water. And the bulge pretty much follows the moon, but the earth is rotating under it, okay? So that's why you have a tide every 12 hours, by the way. When the earth is in this position, you have a high tide. When it comes to this position, you also have a high tide. Now, what happens, however, this bulge keeps following the moon around. But here's what's interesting. The bulge itself, the moon pulls on the bulge, and as a result, it acts like a brake on the earth. And the long and short of it is, the tides that the moon raises on the earth slow the earth down, so it is not spinning as fast as it could. In the past, even about 400, 500 million years ago, actually, the earth was spinning faster, that you had about 420 days as the earth went around the sun, rather than 365 days. In other words, the earth was spinning once about every 22 hours. And the moon has slowed it down considerably. Okay, so that's the case. So what? Here's the so what. The combination of the heating of the earth and the rotation of the earth is what gives us winds on the earth. And it turns out that if the moon were not around to produce the tides, to slow down the spinning of the earth, you would have wind speeds on earth about 1,000 miles per hour. Now, it doesn't mean that one could not exist.
100 or 1,000.
Did I say 100 miles, 1,000 miles per hour? Mistake. 1,000 mile an hour winds. Now in the upper atmosphere, you get some very, very fierce winds. Not so much here on Earth, but the Earth winds would be 100 miles an hour is enough. But of course, we experience that in hurricanes. I missed a zero here. Thank you. 1,000 miles an hour, and you can see the wind effect of this poor tree with the prevailing wind coming in off the ocean. If we existed, we'd probably be crawling on all fours very close to the ground. You know, you stand up and woof, back you would go. So it wouldn't make life impossible on Earth, but it sure makes it easier to exist on Earth. So this is where the moon comes in very handy. But then there's another thing that is also fairly subtle. How many of you have had a top? You know, you spin it, and what happens? It spins for a while, then it starts doing this. And then all of a sudden, clunk, it falls. Okay, this rotary motion that you see here illustrated is called precession. And all tops do that. Well, what is the Earth? It spins on its axis. It's nothing more than a top. What does that mean? Interaction of the Earth, the tilt in the axis, and the sun, and the moon, what you have is precession of the Earth. And so, if the Earth is a top, here's what it looks like. The Earth's axis now is pointed towards the North Star. What it does, if you were to follow where the axis of the Earth is pointing over the course of about 24,000 years, what you would see it make a circle. In fact, if you look very close to the North Star, there's another star that's semi-bright. It's called Thuban. And when Abraham was walking the Earth, the North Pole would have been Thuban, not Polaris. The North Pole that we have now. Again, it's this precession. There's another thing going on, though, as well. Not only does the orbit, the tilt, the axis, not only does the axis precess, but you also have what's known as nutation. So as it precesses, it does this as well. So I'm trying to point out what it's like. This, however, is not a very fast motion on the Earth. Here's what's interesting. we did not have a moon, the Earth's precession and nutation, wobble if you like, which is a combination of nutation and precession, would be chaotic. It would be weird. And here is what Mars looks like. This right here is now, this is about 10 million years in the future, 10 million years in the past. And you can do this mathematically. It's very straightforward mathematics. And this gives you an indication of what Mars is doing. Okay? Notice the tilt away from the vertical can be as high as 30 degrees and down to about 5 degrees. And so with the Earth, actually the tilt, you have the precession, you have the tilt, but it varies from about 22 to 24 degrees. Usually we think of 23.5 as the average. So it's precessing, it's nutating, but then if you block all that out and just look at the axis and the point of the axis, it does this. What does Mars do? Like so. Here's what the moon has done in terms of the Earth. This is the range of variation of the Earth. Now, again, you say, so what? Well, the so what has to do with the seasons, which I will bring up. And so what you have now is the moon has stabilized this chaotic wobble that you would normally have in the Earth. And that has a bearing on the seasons, which I will mention presently. The Earth's tilt in the seasons. Remember, the tilt varies very little. But suppose it varied a lot. What would that do? Well, let's take a look at how the tilt affects the seasons. The sun is off to the left, and during summer, the North Pole is pointing towards the sun, and so you get direct light on the Earth. And during winter, the North Pole points away from the sun, so you have winter in the North Hemisphere and summer in the Southern Hemisphere, okay? We know how that goes. Now, here's what's interesting. When you take a look at the other planets in the solar system, you can see what their tilt axis is. Here's Earth, about 23.5 degrees now, and with slight variation. Venus is almost straight up, but interestingly enough, for some reason, Venus sort of spins the other way around for reasons that we don't totally understand. Mars is pointed about the same as the Earth presently, but Mars varies considerably. Jupiter, almost straight up. Saturn, a little bit like the Earth. Neptune, a little bit like the Earth. Look at this guy in here. Uranus, or Uranus. There's no nice way to say it. Okay, that's just the way the planet is named. Here's what the seasons would look like on Earth if we had the same tilt, almost 90 degrees. In fact, it's more like about 96 degrees, Earth, that Uranus has. And it would look like this. Here's summer. Notice that the pole points directly towards the sun. Meanwhile, the planet is spinning around its axis. But notice you would not have day-night. You would have constant daylight on the North Pole, constant night on the South Pole. You come around here, it'd be exactly the opposite. You would have summer on one pole, because it would be hot, you would have perpetual daylight. On the other pole, it would be perpetual night. It's only when you get to what we call the equinox, in between, that you have a day-night sequence. What do you think the temperature variations would be on the planet under those situations? Great variation. No sooner do you get used to being hot, all of a sudden, next half year, it's cold. And then no sooner do you get used to being cold, all of a sudden it gets really hot again because you have the direct light. So unless you're able to move very quickly back and forth, or else maybe if life formed, it would be right along the equator. It would be difficult to have life as we know it under those kind of circumstances. So the tilt of the axis makes a difference. And now as we speed along, we have to look at the right star. We need the right star, and we're lucky because we only have a single star. By the way, you wonder what these things are. These are called sundogs. Actually, the reason I give this picture is because I'm very proud of it. I took it myself. This was one morning in February, about a year or so ago, excuse me, when we were at a cabin up in Canada, which is north of International Falls. The temperature at this point had warmed up to 12 below. It was 25 below earlier. And it is so cold that what you get is, with the little moisture that's left in the atmosphere, you actually get tiny crystals of ice that are forming. And those ice crystals act like prisms. And so what you're seeing is the light from the sun hitting the prism and then refracting towards us. And so you get this. But anyways, our solar system is unique in that it has a single star. Most stars in our galaxy are double stars and triple stars. Now, the reason this is important is because orbits around double stars are chaotic. It's difficult to have a stable orbit around a double star. A single star is much easier to have stable orbits. And so the fact that we have a single star is important. Second, our star is not very active. Some stars are very active. They are constantly emitting what we would call here a coronal mass ejection. That, by the way, can come all the way to Earth and really mess up our communication systems. Not to mention all sorts of cosmic rays that can come off the sun as well, especially during great number of sunspots. We are in a lull at this point. But you also get these massive ejections that come off the sun that are charged particles, and they interact with our atmosphere, form huge electrical currents that again can destroy our electrical system. So we need a single star for orbit stability, but we also want a star that isn't too active. Second, we want a star that's not too massive. Sounds like the Earth, doesn't it? But here's why. This is a standard diagram that astronomers use, the so-called Hertzsprung-Russell diagram, and all it does is a way of categorizing stars. And the thing to remember is there are stars that are extremely large and extremely bright. Sort of like students at Gordon, the bright part. And here, there are stars that are very small and very dull. Like other schools, okay? So, but here's the thing that's interesting. The large stars last a very short time. You say, wait, I don't understand it. There's no more material there. It should last longer. No, because the larger stars burn the hydrogen into helium for their power source at a much faster rate than what our sun does, and a much, much faster rate than what these stars do here. These stars may only last a few million years. These stars down here, some of them can last hundreds of millions of years. Hundreds of billions of years, sorry, hundreds of billion. What about our own sun? Well, maybe 10 billion year lifetime. And we are about halfway through. This is where the sun is located. And, but why is this important? And here it is. If the sun were 20% more massive, you say, oh, there's more material there. It should last 20% longer. No, it would have burned out by now. That's the relationship that you have, a very large relationship between the lifetime and the amount of material. So if the sun were 20% more massive, it would have burned out by now. Not very good for Earth. On the other hand, if it were 20% less massive, that would make it a small, dull, red star. Well, in order to get the heat that you need on the Earth, what would have to happen to the planet? Earth would have to be a lot closer. Then you would get what's known as tidal lock. You would have the same situation with the planet that you have now with the moon. You know how the moon only has one face towards us? You never see the backside of the moon from the Earth. It would be the same thing with the planet with respect to the dull red star. You'd only see one face. And what would mean is that one face would get very warm and the backside of it would be very cold. Not impossible for life, but difficult for life. Now, what we are, so the sun, the sun's age is important, as this diagram shows. what we have here is birth, and then here we are now, about 4.5 billion years. In about 9.5, 10 billion years, the sun is going to go through a red giant phase, and the outer part of the sun is going to expand all the way out to Mars. And it's going to be curtains for life. And basically, if the sun were larger, that would have occurred by now. Now, once I was given the talk and I mentioned this, and the person got very excited and said, wait, how long did you say this was going to happen? I said, well, we're here, so we've got about 5 billion years to go before that occurs. And he says, oh, thank you, I'm relieved. I thought you said 5 million. Well, interestingly enough, though, when that expansion takes place, and you have the red giant phase, which, by the way, lasts only about 500 million years, as opposed to 10 billion years for our sun, then you would have a new habitable zone that would include Jupiter and Saturn. So get ready. Start moving to the moons of Jupiter and Saturn, and you'll escape the red giant phase here on Earth. Here's another thing that happens once you get to the red giant phase. You get a lot of mass of the sun, the outer layers of the sun begin to get exposed. And those layers are very hot. And you can imagine if those layers were coming by the planet, that would be the end of life, because we're talking about several thousand degrees for that material. Okay, are you with me? Give me a few more minutes here. Here's the other thing that's very interesting. This still isn't math, okay? This is just a graph. Kind of backwards. Here we are now, and here we are 4.5 billion years ago. This is the brightness of the sun, what we call the luminosity. It's the brightness of the sun compared to what it is now. So now you look at the sun, you say, how bright is the sun with respect to the sun? Okay, today's sun is just as bright as the sun, i.e. 1. The ratio is 1. When you go back 4.5 billion years, the sun was only about 70% as bright as it is now. Through time, the sun has increased, well, from 7 to 10, almost 50%, about 40%. Brighter now than what it was when it formed. This is known as the faint young sun paradox, and here's the paradox. Here's what is so interesting. Again, we're dealing with the role of carbon dioxide. And what you have here is a curve, and the blue curve is the amount of carbon dioxide, and the brown curve is what I showed before, is what's happening to the sun. And notice what's happening is that as the sun increases in luminosity or brightness, the amount of carbon dioxide, which by the way was enormous early on, here it is. This is the ratio of carbon dioxide to the present. It was almost about 10,000 times higher than what it is now. Now we're down around here, but the carbon dioxide decreased. I mean, it's ups and downs, but it's decreasing. And here's what's interesting. Here's the young sun, the young faint sun paradox. If the sun had stayed at 70% and the carbon dioxide dropped, in other words, if the sun had stayed at 70% brightness of what it is now, and the amount of carbon dioxide decreased to where it is now, Earth would have frozen. On the other hand, initially, if the sun were as hot as it is now, with all the carbon dioxide that it has, we'd have another runaway greenhouse effect. And somehow, the decrease in the carbon dioxide just balances the increase in the brightness of the sun to give us a fairly stable temperature over 4.5 billion years. What did it? What brought down the carbon dioxide? You see anything in this picture that might do it? Plants. The origin of life that started eating up carbon dioxide, emitting oxygen, and it was just at the right rate so that the carbon dioxide decreased as it was being absorbed into plants, as the luminosity increased. And that is the young sun paradox. Okay, CO2 and life I've already mentioned. The slow evolution of the sun just balanced the appearance of life so as to keep the temperature constant. I have 2 more minutes to go, so bear with me, or else. The role of giant planets, and with this we will quit. Here is an illustration of the size of the planets. And by the way, if Saturn and Jupiter look a bit squished, it's because they really are a bit squished because they rotate very quickly. And so they're a little fatter in the equator than what they are at the poles. And here's poor little Earth. By the way, your trivia for the day is the following. Jupiter is 10 times the size of Earth, and the sun is 10 times the size of Jupiter. I'll let you figure out how much more the sun is than the Earth. At any rate, here's what's interesting. There is a lot of space junk in the solar system, especially the early part of the solar system. And what do we mean? There was a lot of leftover material when the planets formed that was flying around the solar system, and every now and then, bam, one would whack into the Earth. And I mentioned one already that was large enough to form the moon. The stuff is still there, especially illustrated here, but also especially in the form of asteroids, the small bodies that are between Mars and Jupiter, but some of those have elliptical orbits and they come within the orbit of the Earth. And every now and then, one of those objects hits the Earth. And here is a real possibility. This looks like I drew it with my left hand or something, but it gives the illustration. And here is a remnant in Arizona, a meteor crater that's about 4,000 feet wide. It doesn't mean the object itself was that wide. The object itself was probably about 1/10 of that width, but it hits at about 75,000 miles an hour, and an enormous explosion takes place. In fact, explosions can be large enough to destroy life. And this appears to be what happened to destroy the dinosaurs back about 65 million years ago. But that's a different story. Anyways, here's the point. If we did not have Jupiter at least, and Saturn, to act like a slingshot that grabs these things gravitationally and throws them out of the solar system, we would have far more impacts on Earth, enough that life could get destroyed. And so the large planets also help. So these are just some of the things that are necessary for life. Let me conclude. Freeman Dyson, very famous physicist, probably in his 90s now, who was at the Princeton Institute for Advanced Studies, and he says the following, again, no theological bent here. As we look out into the universe and identify the many, what he calls accidents of physics and astronomy that have worked together to our benefit, it almost seems as if the universe must have, in some sense, known that we were coming. Kind of interesting, huh? And Scripture puts it a little differently. Thou, Lord, in the beginning has laid the foundations of the earth, and the heavens are the work of your hands. And the evidence for design is there. It enhances our understanding of Jesus Christ, because after all, Colossians says that all things have been made through him and for him. John 1:3, all things came into being through him. So here again, we find out something about God's creative activity and his wisdom. And then again, remember, the evidence will convict us if we fail to see it. This goes back to Romans chapter 1. And with that, I thank you.